Okay, we can get started, everyone. And okay, just letting one more person in. Hey, Toby. All right, almost full class. Good job. All right, welcome back, everyone. Hopefully you had a really good week. Today is the last class. So before I start, today is the last class of the first term. And so there is a break next week before we start our second term classes on February 6th, I believe. So that's in 2 weeks. Yeah, so next week there's going to be a break for you guys before you start, second term classes in 2 weeks. So this is the last class of the first term. And today we're going to learn more about circles, circle geometry. So let's dive in. All right. So just a review, recap what are circles. Circles are polygons with an infinite number of edges. So we don't call this like one curved edge. We call it an infinite number of like straight edges. Like even though they have like no length whatsoever, we just call it like an infinite number of edges. And if you combine all of them together, it looks like one curved edge. So that's a circle, right? And the circle's perimeter. Letting one more person in. All right. And so the circle's perimeter, so like, the outside, the edges, if you count all of them, like count the length of the edges, this is called the circumference, right? This is an important term called the circumference. It's the perimeter of the circle. Each point on the circumference is equidistant. Is also an important term, which basically means the same distance. So equidistance away from a point called the center. So the center of a circle, if you see my mouse, it'll be around here. Get a pointer. So somewhere around there. That's the center of the circle. And each point on the circumference, so say took this point, connected to the center, same distance no matter what, right? And this distance, we call this the radius. So distance between any point on the circumference and the center of the circle is called the radius. And then the area of a circle is pi r squared. And then the circumference of the circle is 2 pi r, where r is the radius of the circle. Right? So those should be some review. Any questions about these? Any questions about these concepts? No questions? Nothing in chat? Okay, let's move on. Let's just do one simple problem. What's the radius of a circle whose area is 125 centimeters squared? Right? Give you guys a few seconds. So remember, area is pi r squared. We need r. So what's r? Somebody tell me. Anyone have an answer? Oh, did you use a calculator? Wait. Okay, you know what? Let's try this out together. Actually, it was just a simple equation, right? Hopefully this loads. Ooh, it's taking a while. There you go. Okay. All right, simple equation. So we have area is equal to pi r squared, and this area is equal to 125. All right. So you just want r by itself, right? So it's some simple like equation moving around like equations and stuff. So we divide both sides by pi. So then we get r squared is equal to 125 divided by pi. Yeah, I realize that the answer is not going to be a nice number. We're going to deal with it. And then we're going to just take the square root of both sides, right? So that means the squared term in the r is going to be gone. So then we have r is equal to, so 125 divided by pi in the square root. If you want to simplify this further, you can take the square root of 125, that would just be 25. And that's just divided by pi. Can't really simplify square root pi any further. So just leave it like that. Right? Any questions about this? No questions? Okay, this is not like the meat of our entire topic for today. The meat is coming in the next few slides. Okay, before that, let's look at some special side lengths inside a circle. So we looked at the radius, right? So this is the distance between the center and one of the points on the circumference, right? Now the next important side length we should know about is the diameter. The diameter is just twice the length of the radius, all right? So it passes through the center, but then its endpoints are on the circumference. So 2 points on the circumference are its endpoints. So diameter is 2 times the length of the radius. So we can remember that. Next, we have a chord. So over here, a chord is just a line where its endpoints are on the circumference, but it's not the diameter. So it doesn't pass through the center of the circle. So a chord can be like, say, choose this point and connect it to this point. That's also a chord. But I can't make the chord pass through the center. Otherwise, it'll be called a diameter. So that's a chord. All right, and next term is secant. Secant's pretty straightforward. It's just a line that passes through the circle. It has to cross through exactly at least 2 points. Well, actually, it has to pass through 2 points of the circle. So just see, it just crosses through like that. All right, and then the final one, a tangent line. So tangent is a line, is very special. It only touches the circle at one point. So right here, it only skims it at one point before it extends further. Right here, and notice that there's a right angle symbol right here. So this means that the tangent line is always perpendicular to the radius. That's one of its special properties. Just remember that. So tangent line is perpendicular to the radius of the circle. All right. Any questions about these side lengths? These are important. No questions? Oh, let the principal in. All right. Jian Shao. Okay. So now is the meat of our presentation. We're going to look at these circle theorems. So basically, these are like important like properties of a circle that we will learn about. And not only will we learn about like what these properties are, we're also going to prove them as well. So like as I mentioned before in like past presentations, like whatever formulas or like theorems we use, we should know like where they come from in order to get like a better understanding of like how to use them. Right. So let's go on to the first theorem. This is called the Star Trek theorem, or mathematical terms, the inscribed angle theorem. Inscribed just means it's like a fancy word for inside. So it's called the Star Trek or inscribed angle theorem. And basically what states that, say you have points A, B, C, D, where A is the center of the circle, and then B, C, D are points on the circumference, and then you connect the lines like so. So you connect from A to B, then B to D, and then D to C, and then C back to A. So that's why it's called Star Trek theorem. It looks like a Star Trek. You have this angle right here, you call it BAC or CAB. So angle A right here is twice the value of angle D right here. So this is 2A degrees, and then this is A degrees. And yeah, any questions about this theorem before I move on to the proof? So is this, you guys understand what is this about? No questions? All right, I'm going to prove this then. See, I'm just going to remove all these. All right, let's draw a circle. Do not question my artistic skills. Okay, so this is our Star Trek. I'll just call, yeah, we'll just name these points then. All right, so how do we prove this? Well, usually in geometric proofs, you're going to need some helping lines to help you get started. So what I'm going to do is draw a line from D to A, just like that, D to A. So it kind of splits the Star Trek shape into two. We have these two triangles right now. All right, now what we can do, we can set some of these angles to be variables. So let's call this angle, oops, here. Let's call this angle X, X degrees. We'll call this one, so at B, Y degrees. All right, here, okay. So what are we gonna do with these? Well, obviously we're going to try to we're going to try to find some other angles as well. So I think it was last week, I forgot what the term was called. I think it was called like angle skipping or something. But like we're going to try to find some other angles inside this Star Trek shape. All right. So what you will notice at first, well, this is very useful. So notice that from B to A, and from C to A, and from D to A, those are all they are all the radius of the circle, because you're connecting point from the circumference to the center of the circle, which means that these are all equidistant. So like these are all the same length. And what this means is that we have some isosceles triangles. So we have DAC, that's an isosceles triangle because we have two equal sides. Same thing for BAD or DAB, DAB. Okay, and so if we have two equal side lengths, we also have two equal angles. So that means that this angle right here is also X because it's an isosceles triangle, right? And then similar thing for the BAD triangle, we have angle Y right here. Okay, so now we have some more intel on these angles. We can also calculate angle BAD and then angle CAD. So these two angles right here. So this is just, remember that angles in a triangle add up to 180. So this is just 180 subtract 2y. It's because we have two angle y's right here. Right? Similar thing for this angle. So CAD, this is just 180 minus 2x. Okay. Any questions so far? Does anyone have any questions so far? Hopefully this is not confusing for you guys. If there are no questions, okay, I'll move on with the proof. So remember, we're trying to prove that angle A here is twice the amount of angle D here. So we know what angle D is now. This is just x plus y. So we'll just put angle D equals x plus y, all right? Now we're given that these two angles are 180 minus 2y and 180 minus 2x. And with angle A, this is a 360. This is 360 degrees. If you count, if you add all these together, it's 360 degrees. So we can calculate angle A right now. I'm gonna do it on the bottom right here. So basically we'll just subtract both of these angles to get angle A. So we have 360 minus 180 minus 2x, and also subtract 180 minus 2y. All right, we can simplify this by a lot, right? So we have 360, we can subtract 180, get 180, then we subtract another 180, so that would just leave us with 0. So no constant term, right? So that's 0. We have a minus negative 2x, 2 minuses become positive, so we just get 2x. Same thing for the 2y. We have two minuses, which become a plus. So this is just 2x plus 2y. And if you notice that 2x plus 2y, I'll just write up right here. This is just 2 times x plus y. Meaning that angle A is twice the value of angle D, right? So 2 times x plus y is twice the amount of x plus y. And that's the proof of the Star Trek theorem. Any questions? Any questions about this? if there are no questions, I'm going to move on. All right. Now we're going to move on to this right angle theorem. All right. So basically, say you have a triangle, DBC, where DB is the diameter of the circle. So I have a note here: DB is the diameter of the circle, means it passes through center A, and C is just another point on the circumference. If you make a triangle, the angle at the point on the circumference C is 90 degrees. So that's what the theorem states, right? And it's a fairly simple theorem to prove. We can just use the Star Trek theorem. So remember, Star Trek theorem is that the angle at the center of the circle is twice the value of the angle at one of the points on the circumference. All right. So here we have the angle at point A. This is just 180 degrees because it's a straight line. This should be twice the amount of the angle at point C. Point C is 9 degrees, and 180 is twice the amount of 9 degrees. And so that's how we use the Star Trek theorem to prove this right angle theorem. All right. Any questions about this? No questions? Okay. If there are no questions, I'm going to move on to a problem. Right here. In diagram below, if angle ABC is 55 degrees, find the value of BAC. Right. Give you guys a couple of seconds to solve this. So you're going to have to use the right angle theorem from here. Oh, just remember the term for like finding other angles is called angle chasing. So that's what we learned last week. It's called angle chasing. Okay. Yeah, so we're going to do some simple angle chasing in here. Ooh, Bob says 35 degrees, which is correct. All right, I don't have to show it on the whiteboard. Should be fairly straightforward. So from the right angle theorem, we know that so in this triangle ABC, angle C would be 9 degrees, right? From the right angle theorem, that angle right there is 9 degrees. So angle C is 9 degrees right here. And then we know that the angles in a triangle add up to 180. So to get BAC, we just subtract 180 by 90 and 55. And when you do that, you would get 35 degrees for BAC. All right. So fairly straightforward. Any questions? Any questions about this? No questions? Let's look at a couple more circle theorems. Okay. So this is just called angles in the same segment. There's not really like a theorem name for this. We just call it angles in the same segment. So what this means is that say we have two anchor points called B and E. We can also make them C and D if we want to, but let's just make them B and E. So say we have these two anchor points, and then from each of those points, we connect them to a point on the circumference. So we connect them to C. So here, from B to C, and then from E to C, we connect them to point C. Same thing with another point on the circumference. So connect B to D, and then connect E to D as well. So what the theorem states is that the angle made from point C, point D, or from any other point on the circumference will be the same. That's what the theorem states. And it's a fairly simple theorem to prove as well. We're going to also use the Star Trek theorem. So say you have, now you have center A included in the diagram. And so you're going to make a Star Trek with angle A. So you're connecting, so you had B connected to C. Okay, sorry. I'm not sure why my headset disconnects like that. So we had B connected to C and then E connected to C. We made angle A. Then we're also connecting B to center A and then E to center A as well. So then we can remember the property of the Star Trek theorem that the angle at A is twice the angle at C. And say if we did this to point D as well, this means that we're also forming a star trek with BAED. This means that angle A would also be twice the amount of angle D. And if angle A is twice the amount of both C and D, that means C has to equal to D. Or say you had another point like O right here. Any other point, the angles would be equal to each other. So we use the Star Trek theorem to prove this, right? Any questions about this? Any questions? All right, if there are no questions, we'll move on to the next theorem. So we're going to look at the tangent lines theorem. All right. So remember the property of tangent lines, that they're always perpendicular to the radius of the circle. So here we have angle OAC is equal to angle OBC. Oh yeah, before doing that, so notice that there's two tangent lines right here. They're both connected to C. So there's a tangent line AC and another tangent line BC. All right. And so OAC, angle OAC, so angle at A, and then we have an angle at B, OBC. Those are all 90 degrees because tangent lines are always perpendicular to the radius of the circle. All right. But most importantly, there's another part to this theorem. We have side length AC is equal to side length BC. This is what the main theorem states. So so if you connect two tangent lines to a circle, the lengths of the tangent lines are going to be the same. So AC is equal to BC. And this is very straightforward, simple to prove if you use congruent triangles. So remember, I think we learned this 2 weeks ago. So remember, there's a congruent triangle property called side. I think it was side angle side, or I'm trying to remember it. Which one are we using? So we have okay. So we have an angle and then a side as well, and then a side. I think this doesn't match any of them actually. But it's easy to notice that these two triangles are congruent, right? So remember, the triangles both share this side length OC. We have OB is equal to OA because the triangles, because these are both the radius of the circle, so these side lengths are equal. And then we also have this angle right here. OBC is equal to OAC. So we have an angle and then two sides. This means that these two triangles are congruent. And so what this means as well is that BC is equal to AC, right? These are the side lengths that correspond with each other, right? Any questions about this theorem? All right, if there are no questions, I'm going to move on. Right, I'm going to move on to a problem right here. In a diagram below, if AC and AB are tangents to this circle and angle BAC is 50 degrees, find the value of angle ABC. Give you guys a few seconds or a minute to figure this out. $65. That is correct. All right, just do a simple calculation right here. Fairly straightforward problem, right? So we're going to use the tangent. Remember the tangent line theorem? It states that the tangent lines connected to one point are going to be equal in length. So we have that AC would be equal to AB, right? And we also have points ABC forming a triangle ABC. And since this triangle has two equal side lengths, this is just an isosceles triangle. I think this is how you spell it. Actually, I forgot how to spell isosceles. It's a pretty difficult word to spell, but something like that. Isosceles triangle. So that means we have, I'll just draw it out. So this is 50, and say A was here, C was here, B was here. Trying to find out ABC right here, and it's fairly simple to do. You just do 180, subtract angle A, which is 50, and divide that by 2. Because angle ABC would be equal to angle ACB, because it's an isosceles triangle. Divide that by 2, so you get 130 divided by 2. Oops. 130 divided by 2 will give you 65 degrees. Right? Any questions about this? All right. I think I realized how to prove the tangent line theorem now. We're not going to use congruent triangles. We're just going to use the Pythagorean theorem. So look at triangles OAC and OBC. So these are right angled triangles, right? So they both share the hypotenuse OC. So this OC, they're equal to each other, of course. And then remember, OB and OA are equal to each other because they're the radii of the circle. So that means that you have both of the hypotenuses are equal. So the hypotenuse of both the right angle triangles are equal, and one of the legs are also equal. That means if you use the Pythagorean theorem of a squared plus b squared equals c squared, you'll realize that AC would equal to BC. Right, so that's how you prove the tangent line theorem. Right. Now we have that settled. Move on to a few more theorems. So this is called the cyclic quadrilateral theorem. What this means is that say you have a quadrilateral inscribed inside a circle, so inside a square, all 4 of its edges are on the circle's circumference. What you'll get is that the opposite angles add up to 180 degrees. So this means that if you look in the diagram, we have angle B plus angle D gives you 180 degrees, and we also have angle E plus angle C gives you 180 degrees. Okay? And I'll also prove this. I shall also show you guys the proof. Okay, any questions about this theorem though? Do you guys understand this? The basic concept. I'm gonna assume no questions for now. All right. Let's draw a circle. Again, don't question my artistic skills. All right. So I think we had B, C, D, and E. They also labeled the center of the circle as A. Put it right here. Right? Okay, so how are we going to prove that angle C plus angle E is equal to angle B plus angle D, which is 180 degrees? How do you prove that? As mentioned before, we're going to need some helping lines. So first we're going to connect the center A to each of these edges. Sorry, each of these vertices of the quadrilateral. So connect all of these. What you'll notice is that all of these are equal to each other. Because remember, you're connecting a point on the circumference to the center of the circle. And that's the radius of the circle. I think my headset disconnect again. I think it's because like I'm not hearing anything through the headset and then it just automatically turns off. Not sure why it's like that, but okay. Hopefully you guys can like make some noise once in a while. So yeah, so we connected center A to each of the 4 vertices. We notice that these are all equal in length because they're the radius of the circle. Now we're gonna name some angles. Call this angle A. Let's call this angle B. Call this angle C. And we'll call this angle D. Okay, so we have this. Now we're going to do some angle chasing. All right, so we have a couple of isosceles triangles here. So we have ABC, that's one of them, because 2 side lengths are equal. This means that this angle right here is equal to A. Same for this one. So EAB, that's another isosceles triangle. This angle is equal to B. EAD is another isosceles triangle. So this angle is equal to C. And finally, DAC, or CAD, we have another isosceles triangle. So this angle here is equal to D. Okay. So now what do we do? We're going to make an equation to add all these up. So remember that the interior angles in a quadrilateral add up to 360 degrees. Okay, just note that. So then we're going to make a formula to express that. So here we're going to add up all these angles. So 2A's and 2B's, 2C's and 2D's. So they should all add up to 360 degrees because they form the interior angles of this quadrilateral BCDE. So we have 2A. Actually, let me write it somewhere else. Somewhere more space. So here, 2A plus 2B plus 2C plus 2D. So here you have 2A's, 2B's right here, 2C's right here, and 2D's over here. And they all add up to 360 degrees. Okay. And then now what we're going to do is we can take out a 2 from each of these terms, and we also take out 2 from 360 degrees. So we'll divide both sides by 2. So on the left side, we're left with A plus B plus C plus D. So just draw an arrow right here. Equals 360 divided by 2 gives you 180 degrees. Okay, now how does this help us? So we have 180 degrees right here, and the theorem states that opposite angles, so angle C plus angle E, angle B plus angle D, add up to 180 degrees. How does this help us? Notice that, so say we have angle C is just A plus D, right? So this is angle A, this is angle D. Here we have angle E. Angle E is just B plus C. So if you add all these together, you have A plus B plus C plus D. That gives you 180 degrees. So you have one of each variable to get you 180 degrees. So that means angle C plus angle E equals 180 degrees. And then we have a similar argument for angle B and angle D. So angle B is A plus B. Angle D is equal to C plus D. And we have A plus B plus C plus D once again to get you 180 degrees. And that is the proof of cyclic quadrilateral theorem. Any questions about this? There are no questions, so I'm going to move on. Okay, I think this is the last theorem we're going to learn today. Oops, this is called the intersecting chords theorem. Okay, so say you have 2 chords, AC and BD, and they intersect each other at a point called S. So what this intersecting chords theorem states is that AS, so side length AS, multiplied by side length CS, is equal to DS times BS. So product of AS and CS is equal to the product of DS and BS, right? Any questions here before we move on to the proof? Okay, there are no questions. Going to the proof now. Okay, let's draw two chords. Call this A, C. Here's B, D, and S. Okay, so like with our other circle theorem proofs, we're going to need some other lines to help us. What we are going to do is connect A and B, and we're also going to connect C and D. And what we are going to do here is use similar triangles, right? So remember with similar triangles, all the angles are equal to each other. So corresponding angles are equal to each other. And then the corresponding ratios of side lengths. So here you would have like AB divided by CD. You also have BS divided by CS. And you also have AS divided by DS. Those ratios would be equal to each other. Okay, but first we have to prove that these two triangles are similar though. Okay, so let's get to that. So first thing we notice is that we have some opposite angles. So we have angle ASB right here. And we also have CSD, angle CSD. These are opposite angles, and as you know, opposite angles are equal to each other. Therefore, angle ASB is equal to angle CSD. Okay, I'm gonna use a thinner pencil now. Okay, so we proved that one of the angles are equal. For similar triangles, we only need to prove two pairs of angles, because they'll automatically make the third pair equal to each other. Okay, so how do we prove? Now, how do we prove the second pair? We're going to have to use one of the theorems in the past slides. So if we go back to this one, angles in the same segment. So remember, you have two anchor points, and you connect those to a different point on the circumference. And notice that all these angles will be equal to each other. Okay, so we can use that here. Say we use angle B and angle C as our anchor points. So what this will prove is that they're connected to both um, vertex CD and vertex CA right here. So if we use the angles in the same segment theorem, this will prove that angle CDS or CDB, let's connect them to S for now. So CDS would be equal to angle BAS. Okay. So we have two pairs of angles. Automatically proves that the third pair of angles would also be equal. But we can also use this same theorem to prove the third pair if we made angle D and angle A as our anchor points instead of B and C, right? So I'm just going to write it down anyway. So we have DCS would be equal to angle ABS. So here we have proved that triangle ABS is similar. Similar is using this squiggly line, similar to triangle CDS. There you go. So we have proved that these two triangles are similar. Remember, in similar triangles as well, the ratios of the corresponding sides are equal to each other. So we need the side lengths CS and AS, and also BS and DS. So let's figure out what we can do there. So BS would correspond to CS. It's pretty obvious if you look at the diagram. BS will correspond to CS. So BS corresponds to CS. Sorry about that. Okay, so that means that we can write a ratio for these two side lengths. So BS divided by CS would be equal to, so BS we got from triangle ABS. So that means the numerator, we have to use a side length from triangle ABS. The next side length we're going to use is AS right here. So we're going to put AS in the numerator, and this corresponds to side length DS right here. Okay, so now that we have these ratios equal to each other, now we can cross multiply. So we're going to multiply both sides by CS and multiply by DS simultaneously. So times CS times DS. Okay, so what cross multiplying will allow us to do is basically we'll move this denominator to the right side, and then this denominator ds to the left side. That's how cross multiplication works. So that means we're left with bs times ds equals to as times cs. And this is exactly what our proof entails. Let's go back. As times cs is equal to ds times bs. Yep, and these sign lengths match. So that proves our theorem. Any questions about this? No questions? Okay, these are all the circle theorems I'm going to be covering today. There's actually a lot more that you can probably search on yourself, but I feel like these are the most important ones to teach for you guys. So yeah, there are many other theorems that you can learn on your own. You just like type up circle theorems like online, and it'll just give you like a list or something. So you can learn those on your own time. But for our lesson today, we won't be using those. Okay, so let's look at a problem. So find the value of x. And we'll just do this together. Might be a bit complex to do it on your own. Like if you're just doing it in your own head, it'll be pretty complex. Okay, so let's look at that problem again. So we're going to have to use the intersecting chords theorem. This means that DE times CE is equal to AE times BE. Let's write that down. Okay. AE times BE. Okay, yep, I got that right. CE is X. DE is X plus 12. It's AE. AE is X plus 8. BE is X plus 3. All right, now if you want to solve for x, we should expand all of these products. So let's expand the left side. So this is just x times x is equal to x squared. And we have also x times 12. This gives us 12x. So x squared plus 12x. We're also going to expand the right side. So x times x gives you x squared. X times 3x gives you 3x. And then we're going to multiply 8 by x plus 3. So 8 times x, 8x. And then 8 times 3 gives you 24. All right, so we're going to simplify the right side. So we can combine 3x and ax to get 11x. 11x plus 24. There you go. Okay, so now we're going to have to isolate x. So let's move all of the x terms to the left side, and we'll keep the 24 on the right side. So 24 is the only constant term we have in this equation so far. So we're going to move all these to the left side, just like that. So the x squareds will cancel out, and we have 12 minus 11x. So 12x minus 11x would give you 24. This is just x. X equals 24. And that is your final answer. Right? So x is equal to 24. Any questions about this? And you can also double check just by like substituting x back into the equation right here. So I'm gonna try it by myself actually. So we're gonna do 24 times 24 plus 12 is equal to 24 plus 8 times 24 plus 3. That should equal to each other. I'm just gonna double check quickly. Yep, so they're both equal to 864. So x is equal to 24. QED. Any questions about this? Before we jump into some more problems. Any questions? Oh, yep, Bob, you got it. Nice. Okay. How many problems do we have? We have 3. Okay. Look at the first problem. So AB and BC are tangents to the circle with center O. Point D, right here, is a point on the circumference. So if angle ABC is equal to 65 degrees, what is the value of angle ADC? I'll give you guys a minute or so to figure out yourself. And if you have an answer, please let me know. No answers yet. I'll keep waiting. Angle ADC. Does anyone have a value? Anyone have an answer? Oh, Changao and Yiling got 57.5 is correct. Good job. Let's look at it together. Okay, so here's a diagram. Let's draw it out. That's an awful circle. There you go. Let's connect it right here. The center of the circle. And we have this. So this is 65 degrees. Okay. So this is just an angle chasing problem. And we're going to have to use a couple of circle theorems in here. So first circle theorem we're going to use is that remember that we have some tangent lines right here. So this was point A, B, C, call the center O, and then this is this point here. Okay, so we have AB and BC. These are tangent lines, and we know that tangent lines are always perpendicular to the radius of the circle. So AO is a radius, and OC is also a radius. This means that this angle right here, so OAB and then OCB, these are both 90 degrees. Right, and now if we want angle AOC, so this is the angle we're aiming for, AOC. Should write in thinner pencil, thinner ink. So AOC. Remember that this is a quadrilateral. ABCO. This is a quadrilateral, and the angles in the quadrilateral, interior angles, add up to 360 degrees. Well, exterior angles as well, but interior angles also add up to 360 degrees. So basically, we're just going to subtract 360 by all of these angles. So we have a 65, and then we have two 90s. And if you solve for this, so 2 times 90 will give you 180. 180 is just 1/2 of 360, so get 180, subtract 65. That will give you 150 degrees. 115 degrees. Sorry. And so now we have AOC. Now what we're going to use is the Star Trek theorem. So we have ADCO. It forms like a Star Trek shape, and we know that angle AOC would be twice the value of ADC. So if we want ADC, we just divide the value of AOC by 2. So just 115 divided by 2. And if you want to write it as a decimal, it'll just be 57.5 degrees. Okay, this is our final answer. Any questions about this problem? Okay, if there are no questions, I'm just going to move on over here. So find the value of angle AED in the diagram below. Give you guys a minute to figure this out. Oh, forgot to mention that. So point C is the center of the circle, and then BD is the diameter. I mean, it looks kind of obvious from the diagram, but just to let you guys know. Yeah, this one's a bit more tricky than the previous one. Anyone have an answer so far? Anyone have an answer? Elaine says 108. I think that's correct. Good job, Elaine. Yeah, that's correct. Let's take a look. Okay, running a bit out of time, but that's okay. Right, so what do we have here? Two triangles. We have a triangle going here. We also have another one going right here. Okay, hopefully I can fit these values. Okay, I'll just draw a line just to label them. So this is 31 degrees. This is 18 degrees. All right. And label the points. So center C, A is right here. This is B. And we have D as the other point on the diameter. And then this is point E. Alrighty. So this looks like a mouthful at first, but we can use some circle theorems to simplify this, make this easy. So what we notice is that, so remember BD is the diameter of the circle, and we also have triangle BAD. So remember we use our right angle theorem, and this would mean that angle BAD is a right angle because of the right angle theorem. All right, so this is a right angle. Now what we can do, well, we can go for this two ways. So we can try to find this angle right here. So we have ADE. We can try to find that angle using cyclic quadrilaterals, and then we get our angle E because angles in triangle add up to 180. Or we could try finding angle B right here. So ABD, we try finding that first, and then use cyclic quadrilaterals to get our angle E right there. Let's find angle B. I think that might be a bit easier. So we have 18 plus 90 plus angle B gives you 180 degrees. So this means that B, oops, let's use thinner pen, thinner ink. B would be equal to 180 minus 90 minus 18. So 180 minus 90 will give you 90. 90 minus 18 gives you 72. So B is 72 degrees. All right. And now notice that ABDE is a cyclic quadrilateral. So all four of its vertices are on the circle. Okay. So this means that we can use the cyclic quadrilaterals property where opposite angles add up to 108 degrees. So this means that to get angle E, we would subtract 180 by angle B, because B and E are opposite to each other. So 180 minus 72 gives you 108 degrees. All right, so this is our final answer for this problem.